Oh, it's my great honor to speak at the Vienna Schrödinger Institute. So this work is actually mainly based on this paper posted last month or so, and some upcoming work. But the previous work collaborate with several people is very important. I use data because there are many past experience and also research build up. But to highlight is a postdoc, Juven Wang. She is from YMSC in Beijing, and there are some work done in this paper about Cobordism group calculations, and previous work done with Xiaogang Wen and Edward Witten on USU2 anomaly also will be somehow important. And there's a paper by with Wen on this regularized chiral gauge theory on lattice proposal and also Cobordism group check. Okay, so this is a bit technical, but let me try to start from something easy.
Yeah, Juven, sorry, I was wrong. You have 1 hour, sorry.
Oh yeah, and there's something, okay, I hope I still can. Okay, so I also appreciate some conversation with people like Joe, Man, Nakarin, Mingo, Kenaro, Pablo, and Nati, Cyber, and also Ryan, Ivan et al. For some past conversation and some collaborations. And to begin with, because we are in Vienna, so vielen Dank für die Organisation und Koordination der wunderbaren Konferenz. Es ist mir eine große Ehre, für das Erwin Schrödinger Institut in Wien zu sprechen. Einige Leute kennen mich vielleicht nicht aus meiner Selbstständigkeit. Was ist JW? What is JW? Juven Wang, and just wondering, and you may not know me, but it's job wanted. So in the job searching process, it's like people trying to separate people in the group. Like, do you do math or do you do physics? Or do you do condensed matter or high energy theory? So it's a discriminations. If you're not particularly associated to a certain group, and sometimes people will push you to the other side, say, oh, you should find a job in the other side. And some condensed matter people say, you probably should find high energy theory job and field theory job. And high energy people say, oh, you do condensed matter, you should find a condensed matter job. In the end, people like me have no job. And in contrast of discriminations, try to separate people, distinguish people, is a unifications. And unification is a concept that Ludwig van Beethoven will be very appreciate as he write the symphony and also a very late of the string quartet in 1826. And he will be very fit to the topic today. He write the following in the motive of the last movement of this string quartet. He say, Der Schwere was Anschluss muss es sein. Es muss sein. He says that the heavy decision is a very difficult. So difficult and heavy means high energy and gapped in some way, very heavy. It must be, it must be. So I would like to provide a connection to this string quartet that I love very much. Okay, so unifications. Maxwell in 1985, he unified electric magnetisms and light. Glashow, Salam, Weinberg in 1961, 60s, and there's electric and weak interaction unifications plus strong force together. It will be a strong standard model in 3+1 dimension. I will also denote as 4 dimension space-time. The Grand Unification theory, as many of you know, starting from Georgi-Glashow in 1974, with SU5 simple legal unifications, and Georgi and these people, Fries and Minkowski, as a SO10 got Grand Unifications. Or got stand for Grand Unified theory, so I'll just say got. And this will be a spin 10 gauge group, including the electro weak and other forces. In fact, there's already other forces in this SO10 or SU5, so it's not quite correct to say 4 fundamental forces, including gravity. So in a simple legal. However, today, the ultra unifications I will try to outline will be all these sectors and plus this beyond standard model, this Grand Unified forces. But I want to point out some topological sectors. So these topological sectors, one might say that, oh, we already have in the standard model like a theta term, a second Chern class C2 of the gauge bundle, like F or F. However, I want to point out it's not the topological theory or topological term I mentioned. It's not the topological set I mentioned. I will point out the topological field theory, especially a Schwarz type, also formulated by Witten of the unitary TQFT. at a low energy somehow will be needed in some way. And below the energy gap is trivial. People say there's a zero Hamiltonian. However, there's a large TQFT gap. Above them, there could be excitation like anyons or anyonic strings. So the real structure in the modern condensed matter sense will be entanglement of long-range entangled topological order for those systems. It could also enrich by symmetry. I also mentioned that some of the theory may also require some anomaly, tuple anomaly cancellations. It might also be useful to think in terms of some one higher dimension, extra dimensional 5 symmetry protected states. Now people already heard SPD states in short. So this could be involved with TQFT. All right. I also mentioned that by the way, is it clear my voice? If it's not, interrupt me. Also mentioned that a previous work with Weyl mentioned ultra unifications in a different context. That's about the unifications by on a lattice by bosons or qubits on a local Hilbert space. And this will not be the context I'll mention today, although it could be useful and related, but it's not the ultra unifications I mean, LDW. It's also disclaimed that it has not yet directly related to string, superstring, and theory. So probably pursued by Witten and others, and Cyber, and not directly related to unification by qubit or emergent principle, so pursued by Wang and others. So this ultra unification is just an extension of a standard model and gut model from a low energy, in some sense, lower energy quantum field theory, plus some heavy topological sector, for this 546 sector. It may be a new direction and a small humble step to the literature, and no Einstein gravity mostly, and no dynamical gravity mostly, until the very end, when all the space-time internal symmetry is gauged. It could be some gravity. Okay, any questions can interrupt. So I will focus on this type of ultra unifications. And the ingredient for mathematicians, which I apologize not writing down the action, but I will point out there will be some Weyl space-time spinner. There will be Yukawa-Hicks-Dirac term, and also could be Marana mass or Dirac mass. And there's also gauge theory. You're familiar with U1 gauge bundle and summing over as Maxwell's theory, or SU1 gauge bundle, Young-Mills, and or spin N, like spin 10, Young-Mills gauge bundle and summing over. And there will be additionally new ingredients unitary for the non-invertible or 5D invertible non-invertible TQFT. Okay. So I hope this ultra unification right now is clear. So we live in this world with like an energy level that's like several floors, starting from what we are made of electrons and quarks, U and D from a bound state of nucleons. And these are below the energy scale, like 200 MeV, mega electrovolts along the QCD. And the neutrino, so far details, left neutrinos, mass eigenstates is actually much smaller than electron volts. However, the 100 volts, 100 gigavolts GeV to 100 to 200, 300 GeV, there are many scales like Higgs, top quark, and standard model symmetry breaking, Anderson-Higgs mechanism. It's good to find an analogy for this will be some kind of a superconducting effects of the Higgs mechanism in the standard model. It's a CMP high energy theory analogy. Well, at above some scale, there will be electroweak, below the electroweak, Fermi electroweak breaking. That's what the standard model govern. However, above it's not quite clear, and we have a 3 family. So today I would like to point out in this energy range, much earlier before the Planck scale, which is 10 to the 19 GeV, with a large gap, energy scale, there's such many things we can fill in. And this will be a range of scale, even just inside the gut scale, 10 to the 16 GeV, there are many things we can explore. So that's what the topic of my talk. So stay to the very end. You will see what's the meaning of this question mark and how it's related to a Beethoven string quartet. So my other talk will be asked, are there non-perturbative constraints given by the low energy physics at the standard model guiding us towards something heavy at high energy? So we need to be careful about the global structure of the Lie group instead of local electron. Second, we need to know the discrete gauge of global symmetry sectors very carefully, like this finite group Zn. We also need to try to understand all the possible anomaly, especially classified by those one higher dimensional invertible TQFT, denoted as ITQFT later. And there will be associated to 4-dimension anomaly on, for example, 5-dimensional SPT in condensed matter language. There will be perturbative local Z class or or free class anomaly. There will be non-perturbative global anomaly of the Trojan Zn class. And the classification of anomalies, right now, its current knowledge will be related to Cobordism theory. And the fifth, we can ask, are there some dynamical process happening if there's some anomaly? Instead of breaking the symmetry by mass term like Iran or Rana mass, there could be also mechanism when the anomaly is fully matched in the mod, like mod 16 case. The common mechanism people call symmetry gapping rule or symmetry mass generation, or some people also call Kitab-Wundt mechanism. These are known as mass without mass breaking symmetry or mass without mass interaction mass. These are the cases without Hooft anomaly. However, I also need a 6 in some cases, which the anomaly, even if it's not matched, can cancel the anomaly symmetric anomalous TQFT topological order with anomaly. In the lower dimensions, such as the 2+1D TQFT surface of the 3+1D topological insulator, and phenomena in condensed matter low dimension explained by these people. Today we need to go more than lower dimension, go to higher dimension. I also write the energy above standard model, and there will be a connection to the landscape as well. And if all symmetry we are using, try to construct a whole gauge some high energy scale, such as in the quantum graph. There's no quantum here. That's then all the symmetry need to be gauged at some energy scale. We also want to question what happened for those symmetry. Okay, I apologize for the background noise. These are not my fault, just some construction. Okay, so energy hierarchy, I question mark here. But in the very end, please stay till the very end. I'll fill in many energy gaps by many different mechanisms here for the different Grand Unification theory breaking down with different topological sector. So all on the left-hand side is kind of unknown, and part of it you can find in the literature. And many things on the right-hand side was new, and that probably people, including me, and especially this one is proposed just right now. Okay, so, and the one mechanism in contrast about the 4D superconductor effect in Anderson-Higgs, the mechanism for the above the Grand Unification scale, this one will be more like 4-dimensional topological order with some anomaly, topo anomaly and symmetry preserving, and on the boundary of 4-dimensional SPT, which in certain cases can be realized as interacting topological superconductor. So you find the superconductor is formed in standard model in some way. So there is also interesting to find a possible application really for topological superconductor in standard model. But where do we fit the program? So what are known? We need to write down a space-time internal symmetry for the standard model. So space-time is denoted G space and internal G internal. They could be shared by some normal subgroup N. There's an extension of the product is a semi-direct product. And we need to write down the representational matter field and other field, Higgs field, gauge boson in the representation. So I will just say once about the space-time. We will focus on 3-dimensional space, 1-dimensional time via space-time Lorentz spinner. It's a left-hand L chiral space-time spinner. And this in the Lorentz group will be spin 3,1, or in the Euclidean will be spin 4. And they are in the spinner representations. So these are 2 component, left-hand is 3,1, which is SL2C in the complex representations. Sometimes people might like to switch to the 4-dimension, the Euclidean version. And also we need to consider this spinner living on, in some case, living on the 4+1-dimensional boundary. But in the notation we will use for 5-dimension will be Euclidean, which will be spin 5 or USP4 or ST2, pseudo-real representation for component in the representation of space-time. And the reason we do that is that unitarity in the Lorentz, such as 3+1, has something to do with reflection positivity of Euclidean. And there are some theory and previous work proved by Free and Hopkins. What we are trying to utilize is that the classify, for example, D is 5-dimensional invertible TQFT with reflection positivity in Euclidean signature has something to do with anomalies in 4-dimensional reflection positive Euclidean quantum field theory. We hope to use this relation to understand the anomaly in spin 3,1 type of unitary Lorentz quantum field theory. Okay, So not repeat the space-time representation again. So you should always remember the Weyl fermions in these representations. And this will be some full component derived. Okay, but now the internal symmetry of a space standard model, which will be gauged. So you can see this internal is some kind of gauge group later. But right now we regard some gauge bundle for some global symmetry. The Lie algebra locally is SU3, SU2 times U1. I will just say it's Lie algebra 3 to 1 for short. The gauge group indeed will be 3 to 1 ma Z6, and Q can be 1, 2, 3, 6. In fact, all the data from the standard model so far we know for the representation for the Weyl spinner written in terms of, for example, W SU2 for the left-handed fermions, or the right-handed singlet under SU2, and also the quarks are under SU3 is fundamental, and the U1 charge is written in the third component. So here the three component triplet. The first is the fundamental representation SU3, and the second is fundamental representation SU2. The third is the U1 charge in certain convention. So if we try to write down all the data for quarks and leptons, and also including all three families, they repeat themselves, and all these data can fit into the gauge group for all these 4 types. So there's no distinction of which Lie group of a standard model should be. And so we should explore most of them, and I will. The Higgs complex is a complex scalar in the Lorentz spacetime. However, it has a SU2 fundamental representation 2, and has some U1 hypercharge, and it's a single under SU3 color. So this data will mostly not repeat. So we will just take this in mind and then use them. So if we want to go to higher energy in base standard model to gut, like SU5 and SO10, we need to again ask for the Lie group. So precisely the Lie group will be SU5 and spin 10. If we want to include the space-time symmetry, we need to introduce spin D. And the particular invading I'll be discussing will be this type, such that the spin 10 and spin D, they share a fermion parity Z to F, sitting at the normal subgroup spin D, and also sitting at the normal of the spin 10. So that the rotational fermion by 2 pi will relate to the internal Z2 of the spin 10 gauge group. And if I write down all these representations and time frequently, we can try to combine and unite this representation. As Georgi-Glashow told us that we have this 5-dimensional 5-bar representation of SU5, and also the 10-dimensional representation of SU5. When we combine this 3-component D quark and 2-component W for leptons, then this will give you a 5-bar. And if we combine remain, we'll give a 10. And if I include one more right-hand stereo neutrino, which is not charged under any SU2, SU3, and U1, so these are trivial representations. 1 in SU5, we can combine them to a 16 in the spin 10. And later on, so I give most of the representation I need for those models. And we'll skip most of the things about the gauge boson. They are always in the joint, such as SU5 of 24, and they can be written as several decomposition for the branching rule to the standard model sectors like this. So there are 12 gauge boson from standard model A of SU3, 3 of SU2, and 1 U1, and also additional so-called X and Y bosons. And we can also write down the joint for 45, spin 10, etc. And also, we're not discussing the Higgsing, mostly for the consideration of anomaly. Actually, the most important part is those fermions, which can be chiral under the internal symmetry group. Okay, so we already discussed the invading of the symmetry. But one thing is that, can we have an additional global symmetry? One thing people like a lot is the baryon number minus lepton number, B minus L. In fact, there is such a global symmetry, at least in the standard model sense, at least at the energy scale, it could be a global symmetry. And in the SU5 gut, however, it's better to write in terms of a modified B minus L mixed with a hypercharged Y, and such that the writing of this will be like this. I will denote as X, mixing with B minus L and some Y. And the Y is exactly the hypercharge that mix between the SU2's third generator and also the Y. which will be the electric charge. Okay, so it's a U1. So the part of component from Y and combined with B minus L will give me the X, which is like a generalized B minus L in SU5. And if I try to put this into some even higher energy, suppose SO10 or spin 10 play a role, we find, or at least I find, the most natural embedding will be this. It seems like the spin 10 has a center of a Z-fold. Such a Z-fold contains fermion parity. And such a Z-fold seated center of spin 10 can be regarded as part of the discrete subgroup of this B minus L. So at low energy, certainly you can consider B minus L as some U1 global symmetry. And it could be gauged at some higher energy, such as in SU5. But if I want to embed into some spin 10, it's more natural to include only a discrete Z-fold of the B minus L, and which is the discrete X. I'll call this as a Z-fold X. Okay. If I try to ask the quantum number for those SU3, SU2, U1 for all those quarks, and as I already earlier showed, it's like this. So these are fundamental, and these are fundamental for 2 and 3, and trivial for 1, and U1 charge. If I combine them to a B minus L, these are the quantum number, which is a U1 number, so just an integer, so just a number. It could be normalized an integer if you wish by multiply some number, but this will be the convention some high energy people use. If I try to write them in terms of the X of a U1 symmetry, they are written in this way. And the first two of them is d quarks and leptons. They are 3 component, 2 component, which form the 5 bar in SU5. They are -3. The remaining 10 in the SU5 form 1. So they indeed have a defined U1 X charge, but their Z4 X as defined, Z4 X Marfold, they have the same one. Even the right-hand neutrino, the 16th biofermion aided, they are 5 in U1 X, but they are 1 in Z4 X. So they do all have the same Z4 X charge. And also, the twice of this Z4 X will be a normal subgroup, and that normal subgroup is exactly fermion parity. They are also non-trivial under, which because they are all fermions. So that fits very nicely. So importantly, we'll discuss this type of the embedding of the GOP model. And to highlight is that people also work at the Harvard High Energy Group, Mingo Montero, and also some collaborator, and they study a particular type of GOP model like spin d times spin 10. Well, we do also mention this type, but the paper with Juven Wang, or the earlier paper with Georgi-Glashow Wang, we actually study this type, spin d times spin 10 minus Z2 fermion parity. Okay, so we'd like to classify the anomalies associated to this this standard model, and using the concept of the one higher dimensional invertible TQFT. Okay, so how do we do that? So proposed earlier by Cobordism and collaborator, and then systematically formulated by Freeman Hopkins, says the relation I just outlined. So all the time I will not discuss this again. You already remember. The short idea is that we use d-dimensional Euclidean invertible TQFT with some reflection positivity with Euclidean signature to understand the anomaly in d-2, 1 of space-time dimension unitary Lorentz QFT. Okay, this will be 4 dimension. We'll focus on 4D quantum field theory, 5D TQFT. So here we only concern the data called Cobordism group. And this will be a particular data defined in Freeman Hopkins called TP. TP shorthand for topological phase in dimension D. This is like a black box to you right now. Given a space-time dimension and D, and this total symmetry G, including space-time internal, we input this into a black box as a function out to a Cobordism group defined in this way. There's a more common version for this Cobordism group. I should have no torsion here, sorry. And the torsion part of this Cobordism group is the same as the torsion part of this Cobordism group. And there are some conjunction dual relations and plus additional sector, more subtle. However, at least I'm trying to say the torsion part, finite group part, such as Z, N is some integer. The Zn finite group part is the same, but there could be additional Z class differ. So given this G and dimensions space-time, we want to use this Cobordism to classify possible anomalies in 4 dimension and possible topological terms and other things in 1 lower dimension and even lower dimensions. Okay. And actually, I was thinking that out of time, so I will just be very quick on this. We will save this discussion on Cobordism group the calculations to the breakout session. I think it's in session 3. So I will just say that one need to see that the Cobordism group turned out to be a group. The classification for invertible anomaly is actually a group structure instead of other more complicated structure. And the reason in condemned symmetry is that there will be some way of canceling the anomaly by stacking the opposite things. So there is some kind of a identity to be trivial and inverse to cancel the anomaly. And there's some closure of the idea of forming structure of a group. But in terms of the Cobordism group, we are trying to classify the manifolds in different class and with some structure G. And the idea of a Cobordism means like M and M prime Cobordism means that they can be endorse, for example, some structure G, and but as a disjoint union of some one higher dimensional manifold M. If you use this type of thinking, you will see that actually identities just means the empty manifold, and this disjoint union is exactly operations of the group multiplications or sum. And there's an inverse by going M to M bar. And there's easily to see the associativity and commutativity by just thinking about you can just move this around pens and you can join them in different order and they'll be a commutative. Okay, so a particular version for spin Cobordism, I think in physics to use for fermion SPT is proposed by Cobordism et al. In 2014. But Free and Hopkins make it systematic and have a tool to really compute it in mathematics way. So this benefit a lot. We try to do this also including higher symmetry and used for other purpose like Yang series higher symmetry. But for the application for standard model, I think actually the computations based on especially one kind of special sequence called Artia-Herzberg is pursued by Minguo et al. And Davigi and Zhou and Nakarin et al. Well, our method will be more close to Free and Hopkins using atom special sequence. Okay, so this part I think I will skip. I will just say that there's a deformation class of a reflection positive D-dimensional extend TQFT, ITQFT with a symmetry group G, turned out to be classified by some kind of deformation or homotopy class of two spectra. One is called Anderson-Tillman spectrum. The other is called Anderson-Tillman spectrum, and with some suspension shift. And this will be turn out to be a calculation of homotopy group of some Anderson-Tillman spectrum. And detailed calculation will be discussed in the breakout session. All we need to do right now is believe there's a black box given dimension D and symmetry G. We can classify invertible TQFT in those with that structure. In each invertible TQFT, when putting on some manifold, we can use them to detect the non-trivial invertible TQFT for each distinct class. And on the boundary, if the manifold of this theory has, if the ITQFT living on manifold with boundary, then that boundary has an anomaly, and that's all we need to know. Okay. So we just use some trick and to obtain such a result. So the pertinent things will be computing the spin group times space-time times standard model and spin Z4 mod Z2, as I say, in way to spin 10, this one, spin time mod Z2 is this one, and also this type for the SU5. There was an additional discrete sector. I think people care about the algebra will be definitely neglecting this. And also people only care about the algebra will not be careful about the Z2 mod Z2. But it turns out all these things will be important to give rise to anomalies beyond the local perturbative anomaly, captured only by Feynman diagram. Those Z class of anomalies, free class, will be captured by Feynman diagram. But those ZN class, which called torsion or finite subgroup, finite group part will not be captured by one loop triangle Feynman diagram. So these are beyond the perturbative anomaly. And I list down all the data. And there are many information I need to go through one by one. So I will do example by example. But right now I just show you one style all this data can interpret some anomaly. One can check which anomaly is there or not. Depends on you interpret the Z4 as a global or gauged. Then the consideration for the anomaly matrix also differ, which will be shown in the next slide. Okay, so these are the work. I think just say that we are using Adam spatial sequence. I think the other group using Artia-Herzberg. The good thing about Adam is actually a bit more powerful is that we can actually determine this finite group without ambiguity. There are some subtlety for AH spatial sequence where you actually cannot fully distinguish the problem of extension. Something cannot be exactly solved. For example, you cannot distinguish Z4 and Z2 times Z2 in some case. well, the Adam spatial sequence used by Free and Hopkins can really determine this. And another thing is that by looking at some kind of a chart called Adam's chart, we can read the topological term. So that's a powerful part. Okay, enough for the math. So let's go to physics. So anomalies. What are the anomalies? We'll discuss mostly some of them. But in general, if I just consider perturbative anomaly, there are kind of anomaly called dynamical gauge anomaly, which means that if I have a perturbative local anomaly captured by one low Feynman diagram, like triangle diagram, with vertex coupled to gauge field, with this solid link run by this fermion, chiral fermions, you can compute the anomaly coefficients. And if the gauge field are all dynamical, we believe that for consistent quantum field theory, this anomaly, gauge anomaly, must be cancelled to be 0. However, it's not the same for the tuple anomaly. In the coupled background, it's a global symmetry, coupled background field. In that case, actually, the tuple anomaly does not need to be 0. If it's not 0, it just means that there's an obstruction to gauge the global symmetry. But that's a global symmetry. It's okay. In condensed matter, it just means non-inside symmetry. In high energy theory, you can say it's anomalous symmetry or emergent symmetry at low energy. And the third case will be a global symmetry on one vertex coupled to two gauge field. These are original Adler-Bell-Georgi type anomaly, means non-conservation of a current associated to one vertex of global symmetry will not conserve when these two vertices dynamical gauge field. There's also one type of one dynamical gauge field with two global symmetry. We'll mostly focus on the first one, second one, in some cases, the third one in the following. So let's go through example. This will be a review of more textbook example you learn in standard model. Is that in the standard model, you can check, given the global gauge group, how are the global symmetry, the anomaly are possible. So based on the Cobordism calculation, we find out actually there are z to the fifth class of anomaly, and you can write down the 5 of corresponding this triangle diagrams. And so these are the 5 cases. So U1 to the cube anomaly will be written in terms of one higher dimension, ID, ITQFT, Cobordism invariant as first Chern-Simons one form, and C1 first Chern class square. And O, some people write as a 60 anomaly polynomial is a C1 to the power cube, U1 gauge bundle. If I have a 1 U1 and 2 SU2, similarly, just changing the C1 square to C2 SU2 bundle, and there's a 60 polynomial. Similarly for SU3, changing this to SU3 gauge bundle. The mix between U1 and SU3, so you can read actually exactly match the Feynman diagram. And if I have a gravity U1 and gravity square, it turns out this will be related to some kind of invariant, more complicated. Gravity related to space-time, so we have a space-time data here. So in the 60 polynomial, sigma is signature of the manifold, and F is some characteristic to surface. But in the 5-dimensional case, will be a roughly invariant mu and a Pontryagin dual of the C1 U1. So this will be 5D term. So this will check this diagram. If you don't know this okay, just know their Feynman diagram. If you don't know Feynman diagram, you know there's mathematics here. Okay, so the fifth one is SU3 cube. So this will be a Chern-Simons 5 form of SU3. And there's also 6-dimensional polynomial. In certain cases, actually, Witten SU2 anomaly, a global one, Z2 class actually cannot show up. This will be the case when the standard model gauge group mass ZQ and Q is 1 and 3. And this case will be a Z2 class will still play a role. It will be used for the dynamical gauge anomaly cancellation. However, interesting phenomena when Q is 2 and 6, 1, 3 will fuse with Q's 2, 6 Z class. So local anomaly. Global anomaly become local anomaly. I think illustrate well in this paper. But in any case, these are the data obtained. And we can check one by one. It turns out everything will be 0 cancelable dynamical gauge anomalies, we believe, for standard model. And the textbook example, for example, like this one, you compute the U1 hypercharge coupled to gravity, input the U1 data, and then put in everything in. You'll find out that this will indeed cancel. Okay, so these are the U1 hypercharge for the quark. For this first part, and this one U1 hypercharge for the lepton. So these are standard. But now if I introduce the U1 of the B minus L, it's natural to written as a spin C structure. And okay, these are data from here. So we can compute this question of all these things again. And then there are more Z class than earlier, and one can check again. And in particular, we are interested with the B minus L conserved and coupled dynamic gauge field. So this will be a diagram to check. In the case of SU5, we can also have a spin C times SU5 with this U1. The U1 will not be exactly the B minus L, but the extended version B minus L, 5B minus L minus 4Y. This will be the X. Okay, so this will be the diagram to check. Okay, it turns out everything also match. So which means B minus A is almost a good global symmetry, except that two of the diagram actually require something slightly more. Is that if you really plug in, you'll find out that it implies that there's a class of anomaly does not match unless there's for example, a Weyl fermion in a perturbative sense. In the 16 of Weyl fermion is a right-hand neutrino. So this formula only shows that the B minus L current conserved by plugging in when there's a right-hand neutrino, one of right-hand neutrino, or some number. We can ask, well, the U1 B minus L, in some sense, you can also ask, perhaps it can be it could be broken, or perhaps we really have some heavy right-hand neutrino. That's what people believe, a large Marana mass or Dirac mass by seesaw mechanism. So we don't see it at the low energy, but it could be very heavy. So the anomaly can be cancelled. We can ask further, suppose we want to invade the U1 into the Z4. That's why I say that it will be a center of a spin tank. Does this still survive? So the calculation will evolve into compute this. And then we can ask again the anomaly. It turns out that more of the global anomaly will show up instead of all local anomaly earlier. We can examine this. Okay, so just one by one. First of all, I should mention that the Z4 here, there's a Z4 zero-form symmetry, which coupled to a one-form local gauge field related to this B minus L. And however, this will become a Z4 gauge field when I write in terms of spin Z4 mod Z2. And this mod 2 will be a one-form gauge field locally. But this should be regarded as the first cohomology class with Z2 coefficient, AZ2. And they are the generator of this Z-form X mod Z2 fermion parity. So that's a quotient part of this. Okay. It's not the fermion parity part. Okay, it's not normal sample. In this Z2, we can ask what are the anomalies and written in this way. Okay, so it turns out the Witten anomaly will still be there, at least for Q equal to 1, 3, but it will be graded from Z2 to Z4. And we can check still anomaly free. And the term of written Witten anomaly in 5 dimension of the topological Cobordism invariant will be this form. Some eta invariant in 1D and C2 of the SU2 bundle. C2 is a second term class. Secondly, we can also have a 4D Z2 anomaly. And that Z2 anomaly happen when we have a Q equal to 2 and 6 of the SU2 bundle. And this will be mixed with the Witten anomaly from Q is 1, 3. But anyway, this is still anomaly free. And third one of SU3 bundle mixed with U1, the Z4 gauge field, or Z4 mod Z2 gauge field is also free. So everything mostly free. Let me just go to the non-trivial one. Even the SU5 is free, except the Z16 one. And this Z16 one seems directly related to the Z class anomaly that still survive as a constraint that may not be matched. So the Z16 anomaly may not be matched. So there will be a trouble. So what are the possible way to match and to check the anomaly? Certainly when you go to calculation, I showed you this table earlier. And there's a Z4 charge associated to those quark and leptons. You plug in and try to compute the anomaly with a match. It turns out that for example, 3-family generation, for some n family, the anomaly does not match as it will be minus n of mod 16, unless there are some either neutrino, right-hand neutrino, or 16 Weyl fermion, or hidden sector to cancel the anomaly. So the conventional way, actually most people still use is the right-hand neutrino is anomaly observe the anomaly, and it could be either preserved as gapless, but which can be ruled out by phenomenology. We don't see them. And but it could be broken by Dirac or Marana mass, because this mass term will break the Z4. This is kind of chiral in some way, so you will break Z4. And you could turn on a large mass gap, you don't see the neutrino. So that could be explanation people like. However, today we would like to propose it could be new hidden sector. A possibility is that it might be nice to have a Z4 preserved even to the spin 10 scale, a God scale. If a Z4 is preserved, but we don't have a spin, there's a low energy neutrino, other than seesaw mechanism to lead to the mass, is there some other mechanism? So I will call this as a different but Dirac Marana mass, but it's topological mass. This mass is a mass, interacting mass, not from free theory, but preserve Z4 and by anomaly, preserve anomaly as a gap for the TQFT. So this will be a first scenario. Secondly, we can possibly say there could be additional one high dimension, some invertible TQFT, such as standard model live on the boundary. And this could be a Z4 SPT precisely written with some eta invariant of Pondrian duo of this AZ to H field, so it's a 5D invariant. So Z 4D and 1D talk, kind of a Pondrian duo together to 5D. It could also be Z4 is gauged if you believe quantum gravity, no global symmetry. Z4 will gauge, so this will be enriched in some way, and the Z4 symmetry can gauge. And if this is coupled together, you can even imagine the space-time symmetry that detect the eta invariant can also be gauged. And eta invariant can be put on, detected by RP4, for example, and this eta PDA can be detected by RP5, 5-dimensional or 4-dimensional real projective space. And if at high energy quantum gravity or high energy scale, everything is gauged, then there could be something about the gauging of the Z4 symmetry and also the space-time symmetry. And there could be some natural way to couple to gravity. But lastly, Z4 symmetry can still be broken by gap, but this will be very kind of boring, so I will not focus on that. But in any case, it seems like I'm saying something like out of nowhere, but it's not. Actually, I'm using very, I think, as much as rigorous constraint as mathematics can give, the Cobordism constraint, and very solid calculation. So these are not dream up. These are really something, I think, every scenario possible. And just based on phenomenology, we can say something more. I will focus on possible mixing between the right-hand neutrino, which mix, for example, the Raman seesaw mechanism. For example, for some generation of family, maybe 1 or 2 out of 3 can have this mechanism, while the other one can have a symmetric gap. In general, you can just need to combine this capital 1 and this little 1, 2, 3 in some linear combination to cancel the anomaly, because it's a group law. So in general, we can propose any linear combination. We can still have an extra dimension. We can still have a symmetric TQFT. We can still have a Dirac-Monoid mass or some mixing, such that linear combination makes it fit this anomaly cancellation rule. Okay, so this 5-dimensional SPT is given by this Cobordism invariant. But what exactly is this 4D TQFT? It's a long-range entangle, mentioning anomaly. So the method we will use will be some kind of symmetry extension method generalization based on a previous work done with Weyl and Witten. But we need to do a bit more job. And these are ongoing work with Pavel Putro, not sure what he's in audience, and Ryan Rongan. Hopefully we can sort it out. But simple version is the following. We try to understand such a Z16 class non-perturbative global anomaly with Z4 gauge and space-time gravity symmetry anomaly. And this mixed gauge gravity anomaly, can it become anomaly free in some extension G hat and with some finite group K? Again, I'm saying the simplified version. The real version is more complicated. If that's true, we can actually cancel the G anomaly by a K topological gauge theory, but symmetry realized anomalously on this K gauge theory, and that will be a 4-dimensional theory. But for today's audience, I would like to give some simple physical observable bursts to probe for this 5D SPT or 4D TQFT. What can we observe? What experimentalists can detect? What experiment we should do? And it's kind of interesting to ask the following: if those TQFT has long-range entanglement and fractionalizations, they have an extend operator like line surfaces. We can ask the following: the 5D TQFT SPT invertible TQFT is given by this, and 4D TQFT is outlined just earlier in the slide. I didn't write it down precisely, but they just believe they are cycle TQFT. We have formed by atoms, which are quarks, U and D quarks, and electrons. We are all formed by particles, point particle. They form some bound states. But we can imagine whether there's a way we can have some force or connection with this objects formed by some extend objects of lines, surfaces, extend object. If you have some imagination of things, this would have probably more complicated bound states, maybe more complicated than the proton neutron they can find. Certainly, these are just kind of pseudoscience or science fiction, but just thinking about it for a while to say, oh, it could be some extend objects in the 4D TQFT. But let's call this an alien being. Is there a way we can communicate with them other than knowing they could exist by anomaly? So we should know, is there a way we can connect by some force And that force doesn't exist in the standard model. All the U1, SU2, SU3 doesn't directly, the gauge boson does not directly interact this TQFT sector. However, as I mentioned, there's a Z4 symmetry, which can be gauged at high energy. At low energy, standard model you might regard as global symmetry, but again, by quantum gravity, you know that's gauged. So we write down the Z4 symmetry for all the quark and lepton. You find everyone is charged. So every of this particle inside our body, the atoms, the electrons, all have some unknown force to the Z4, which is discrete. It's hardly to sense, it's topological. But we are interacting with this Z4. Imagine Z4 has endpoint. One endpoint can be particle in the standard model. The other end will be a line operators for the Z4 gauge field. How does this Z4 gauge field can end on the other side? Of course, it can end also on our standard model particle, but it could actually be another end be sourced by another charged particle from TQFT. There's indeed a charged object under Z4 that indeed has the Z4 global symmetry. There's a codimension 1 surface operator wrap around some extent operators of one-dimensional lines, such that this link, such as half link, these are two of the S1 loop, or some bromine ring, if it's a theory for more complicated theory. When there's such configuration in the TQFT, actually with a suitable line operator, they can have a non-trivial Z4 charge. So imagine this is a line operator of a Z4 gauge field. On one end, connect to all the particles in our body. On the other hand, connect to the lines and surfaces of the TQFT of unknown sector. And there's an unknown interaction between us, standard model particle, and all the lines and surface on the other side. So there's a quantum communication between us and some unknown being or some unknown sectors in the TQFT. It may not have an intelligence, but anyway, we can call this as a God sector or topological quantum computer in 4 or 5 dimensions. Whatever, you know my meaning. So there's a gradient statistics in Lincoln where in 4 dimension 5D actually has an unknown sector to us in the standard model, but has correlations, kind of a force beyond standard model I call topological force by the Z4 gauge X. Okay, so I have spent so much time, but what's the energy scale I outline other than what I already know? I add one more. I say that instead of all scenario that we have a Marana mass to introduce to right-hand neutrino break Z4 and also match anomaly, we have a TQFT alternative to the Marana mass for the heavy stereo right-hand neutrino we don't observe. And that's the scale here. Because that Z4 is preserved, so it could be a higher scale. Even the Z4 can be broken at low energy if you want. So that will be above the scale of SU3, SU2U1 times Z4 minus Z2, spin times Z4 minus Z2, or also SU5 Z4 times spin times Z4 minus Z2. Above that scale, the Z4 still can preserve, and there is a TQFT topological mass energy gap. So what leave above us heavily unknown are above standard model. We may not detect other than just using the Z4 gauge field that connect us. And no standard model force cannot see us. Even if we collide with them, we don't see them. They could just be around us everywhere. We just don't see them because there's no Z4, there's no standard model force to detect them, but just a Z4 gauge field. Okay. So it could just be around us everywhere. Okay. So right now there are some philosophical question and the existence of a God, though this question might be addressed or maybe asked at least. So space-time internal groups embedding, I already go to the spin times spin 10 minus Z2. But it could go further to the spin 18. That's the kind of things people pursue in the 80s, like Frank Wircher and Tony Z and people here. One thing I would like to mention is that we can embed them into several series. In the past, people discussed dynamical gauge breaking like this pattern. But here, I would like to pursue, other than this type, I also want to pursue something more, is that how do we match and also compute the anomalies for them and try to add some global non-perturbative constraint. It turns out that we can still compute a cobordism group. It's complicated for all this. And then we can ask again whether all the anomalies match. Are there some Tahoe anomaly or dynamical gauge anomaly? And one interesting fact is that for certain case, actually, we require additional matching. Let me just say, I would like to use another mechanism starting from gapping out the fermions in the mirror sector. What I mean is the following. In certain case, the Grand Unification theory can have some, like a spin 10, we have a 16 in the spinor representation, 16 bar. sitting minus in the conjugate, complex conjugate representation. You can imagine if I regularize quantum matter, it's a quantum matter for this theory. One side of boundary has chiral matter, the other side has the fermion doubling. And people try to thinking about this in some quantum theory, but it's not quite understood. Einstein and Preskill introduced, say that we can gap the mural sector by interactions, but those interactions are limited to certain cases. It's not convincing enough. I think the new insight from topological phase, from complex matter development, starting from maybe Kitab and Wang, basically saying that we can still gap the mural sector and without breaking symmetry. People like these people could pursue, and also our paper pursue that, in fact, we can actually gap the mural sector if we need it. Otherwise, there's a mural universe that we don't observe. But what I mean is that there's another mechanism that I want to use other than the topological mass. That's people call some key type of mechanism called the symmetry mass generation in the mural sector. If we do that, we can actually introduce additional energy scale by gapping the mural sector with some gap. And to check whether there is such an anomaly for those theory, it turns out the new SU2 anomaly study with Weyl and Witten turned out to be important because SU2 is a spin 3, and that's a subgroup of spin 10 and also subgroup of spin 18. We can check the anomaly mentioned by embedding to spin 3 into spin 10, spin 18. If we do that, the two new scenario that given in my talk is, one is the symmetry anomalous TQFT already introduced one scale, the other is symmetry gapping rule. This also introduced another two scale. This two scale, one is drawing here, gapping the mural sector to SO18 and gapping the mural sector to SO10. So this energy scale should be above the TQFT that scale I introduced, and also above the unified scale for SO10. And yeah, basically. So they are more energy scale. Okay, so all these things I draw on the right-hand side with blue colors are actually new, kind of new to the literature, especially fitting into more phenomenological ground. But the thing is that this scale is very high, so it's probably still not easy to pursue that. Maybe one still need to figure out possible other details of phenomenology, but in any case, there is such an energy scale related to the TQFT topological mass scale and also the symmetry mass or Kitab one mechanism scale. And we can go through the other route for another dynamical gauge symmetry breaking, such as breaking spin 18 to SU9, and then breaking to SU5 times SU4, SU5 times spin 5. And we can compute the Cobordism group again for those and classify all the anomaly and try to plug in all the representation for the matter field as again the anomaly mentioned. It turns out that the earlier result will be different. There'll be a different type of dynamical scale, or the gapping scale. But anyway, so there are different scenarios one can pursue. But you get my point. So let me summarize. I think I'm almost done. So I discussed ultra unifications, which is a different type of unification that include electroweak, strong, and other forces such as gut, Grand Unified theory forces, plus topological sectors. This topological sector is distinct from what people usually call about the theta term, because those are just the gauge bundle of the second Chern class of the Yang-Mills theory. That's part of the things you sum over in gauge theory. What I'm discussing is not this. I'm discussing the topological sector in the sense of a long-range entangled topological order that below the energy gap at low energy is topological field theory, but above the energy gap have some fractional gap excitations of extent objects. And also possible one extra dimension symmetry perturbative states that can be gauged. The Z4 can be gauged, then it could be enriched, or it could also couple to gravity. And starting from the invertible TQFT, once you gauge, you could also be non-invertible. So it depends on the energy scale, just depend on whether you're looking at the standard model scale or SU5 or SO10 or spin 10. And the equation, as I mentioned, other than the standard model biospinors, Yukawa, Higgs, Dirac, and plus the U1 Maxwell, SU1, Spinor, Yang-Mills. We also mentioned the unitary 4D non-invertible TQFT or 5D invertible non-invertible TQFT, and possibly coupled to some gravity when the space-time symmetry is gauged. The starting point only is the low energy standard model, and then try to get the heavy sector by the Cobordism anomaly. So my summary, our breakout session will be this. The unification has SM Grand Unified and Grand Unified theory plus topological sector. Energy hierarchy, we are asking who live above us and heavily and upstairs. They are like our roommates living in the building. We don't have a force directly into them with them, but maybe they are just Next was a new life made at high energy that we cannot see or detect by a standard model particles, but we can communicate by a gauge Z for X, where there is some line surface operator connect the standard model particle and topological force. This goes back to Beethoven's quote: "Der schwere Gewachsanschluss muss es sein, es muss sein." So the heavy high energy gaps decision is very difficult since in the past, but must it be? Perhaps it must be. And vielen Dank, bleibt gesund und sicher. Thank you for staying tuned. Stay healthy and safe. Thanks. I think that's it.